Encoders. Sort of resemble potentiometers mentioned earlier, but non-contact optical devices. Convert angular position of a rotating shaft into an analog or digital data code. All optical encoders work on the same principle. Light from an LED or infrared light source passes through a rotating high-resolution encoder disk that contains the required code patterns, either binary, race, grey code, or BCD. We touched on grey code last week. Re-emphasise what that means this week. Photodetectors scan the disk as it rotates, and an electronic circuit processes the information into a digital form as a stream of binary output pulses that are fed to counters or controllers, which determine the actual angular position of the shaft. Two basic types of rotary optical encoder: incremental encoders and absolute position encoders. So, the incremental encoder. Look at the diagram now. Coded light and dark pattern on the disk. Okay, we're looking at it in terms that the disk has been straightened out. Usually they are a disk that rotate. It's just easier to perhaps understand. The rotation of the disk could be in any direction. So there's two photodetectors displaced, and therefore that will enable the sensor to detect which direction the thing is going in, because it's actually doing two signals and looking for the displacement between. So incremental encoders, and also known as quadrature encoders, or relative rotary encoders, are simplest to the output is a series of square wave pulses generated by photocell arrangement as the coded disk, evenly spaced transparent and dark lines called segments moves or rotates past the light source. Encoder produces a stream of square wave pulses which, when counted, indicates the angular position of the rotated shaft. So it counts the pulses, an incremental encoder does. So from a given position, it counts how many it's gone. From that position, it knows how far it's moved from its last known position. One main disadvantage of incremental count encoders is when used as a position sensor, as they require external counters to determine the absolute angle of the shaft within a given rotation. If the power is momentarily turned off, or if the encoder misses a pulse due to noise or dirty disk, the resultant angular information will produce an error. So if it loses the count, then it doesn't know where it is. This is what we talked about last week. Under those conditions, it would have to go back to a home position so that it knew its start point, and then it can do a new incremental count from there. Yep. So one way to overcome that disadvantage is to use what's called an absolute shaft encoder. Absolute position. What there? No, that one's still incremental. I don't. Yeah, there's a little bit extra. Typical, it's like I've updated it. Typical encoder disk of a revolution of up to 250 pulses, or 8 bits per rotation. Because of which one comes on first. Yeah. Let's start that up again for the next one. Absolute position encoders. Absolute position encoders. They are more complex than quadrant encoders. They provide a unique output code for every single position of rotation, indicating both position and direction. The coded disk consists of multiple concentric tracks of light and dark segments. Each track is independent with its own photodetector and simultaneously read a unique coded position value for each angle of movement. So there's a separate code for every angle around one rotation. So it uniquely identifies exactly where it is by a unique code. It'll give absolutes. It doesn't matter if it stops somewhere, it'll still know where it is when it starts up again. The number of the tracks on this corresponds to the binary bit resolution of the encoder. So a 12-bit absolute encoder with about 12 tracks, same value as 1 resolution. So if we look at this encoder here, bit A is up the top, then bit B, bit C. It's a little bit difficult to see exactly how that works. But if you look along here, in each of those positions, we start off with effectively 1, 1, 1 here. Bit D goes to 0 there, comes back on 1, but bit C has gone to 0. So each of those, we could write them all in, but they'd all provide a unique code over 1, 2, 3, 4, 5, 6, 7, 12 positions. That is. Well, we got 2 of the 4 units, 2s, 4s, 8s, effectively 16 different positions with a 4-bit encoding. And they can be done, they can use a binary code that will allow a direct input to a PLC, so they go up in binary order. So in 3-bit 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and so on. Okay. Now, the issue with that is, if you've got 2 bits changing at the same time, and they don't change precisely together. So if we look here, this is okay. We've got 1 bit changing there between. Just do that. On that code here, we're only changing this 1 bit. But here, bit 1 is changing back to 0, bit 2 is changing to 1. If they don't do that exactly at the same time, if this 1 here drops out before that 1 comes on, we've effectively moved back to the 3 0 bits position, which would be an issue, it'd be an error. Okay. If we use the grayscale code, then only 1 bit changes at a time. And the grayscale code goes something like this. I'm not good with that magic pen, am I? So having the grayscale like that, where only one bit changes at a time, gets round the issue of having to make sure they time together precisely. However, a PLC or a controller can't understand this directly, so it has to have some other kind of logic circuitry that does a conversion between grayscale and binary so they can understand which code is which, because you want to be able to link this one to position 1, for instance, that to position 2, that to position 3. They don't relate to that at all in binary, so you've got to write some kind of code to convert the grayscale to some kind of other understandable code in those cases. Yep. That the encoder might include some internal circuitry to do that. Okay, depends on what you buy, but the grayscale, the grey code one, means that you have to have some kind of logic somewhere to convert. Alright?